Aaron, it's hard to believe that so many top physicists actually believe in infinitely many parallel universes. While I like how last time we analyzed the three premises that multiverse theory needs in order to explain fine-tuning, maybe we're taking this whole multiverse thing a bit too seriously. I mean, doesn't this sound way too much like science fiction?
Ellie, relax. You can't just reject a theory because it sounds like science fiction. Quantum mechanics sounds absurd, but it's highly supported by a ton of evidence. In the same way, even if infinitely many parallel universes sounds wild, we have to take it seriously and examine the scientific evidence that supports it.
Okay, I suppose you're right. Quantum mechanics does sound bonkers, and we're actually going to discuss some of that craziness in this episode. But it's a well-established scientific theory. I guess we'll just have to leave my preconceptions at the door and see where the science leads.
Right. Not only is that a more honest approach, but we'll also have much more fun that way. It would be a shame to miss out on all the fascinating and wild ideas we're going to discuss just because multiverse goes against your initial intuitions. That's not to say that some things that sound crazy aren't just plain wrong. It's just that sometimes things can surprise you.
Welcome. This is Physics to God, a guided journey through modern physics to discover God. My name is Eli Fader, and I'm an Orthodox rabbi and a mathematician.
And my name is Aaron Zimmer. I'm also an Orthodox rabbi with a deep interest in physics and philosophy. On this podcast, we'll discuss some of the most fascinating developments in physics and make a convincing argument that they point directly to the existence of God.
Before we discuss the various supports multiverse scientists have for the infinite multiverse premise, we need to carefully consider the fascinating yet subtle idea of infinity. Infinity has solid grounding in mathematics, where on a basic level it's used to represent a process that has no limit and therefore never terminates.
For example, you can generate all the natural numbers by starting with 1 and repeatedly adding 1 to the prior number. This process can always continue, as you can always add 1 to any number. Therefore, there's no biggest number, and in this sense you can say that the natural numbers are infinite.
In the late 19th century, George Cantor, the originator of set theory, extended this basic notion of infinity and developed a mathematical system of defining and working with different levels of infinity. For Cantor, infinity wasn't just a process, but could be used to describe an actual mathematical object, like the infinite set of all whole numbers. While Cantor's work was controversial at the time, mathematicians today accept set theory and its levels of infinity in fields of mathematics like analysis and topology.
Nevertheless, accepting the existence of infinite sets in the realm of mathematics does not imply the existence of an actual physical infinity. It's a serious error to equate the two. This is not to say that scientists can't mathematically model an infinite universe just as well as a finite universe. They can, and do, create models of both finite and infinite universes. For example, you can analogously think of a finite universe as closed and curved, like the surface of a sphere, while an infinite universe extends without bounds, like an infinite plane.
Whoa, Aaron. Let's try to keep this simple. The main point is that neither a finite nor an infinite universe is mathematically preferable to the other. However, the mere possibility of describing something mathematically in and of itself doesn't provide support for the existence in physical reality.
I was just trying to give an analogy in 3 dimensions, Ellie, so our listeners have some idea of what a finite and an infinite universe might look like.
Somehow, Aaron, your analogy made things more complicated. Let's move on. Historically, there has been much disagreement about whether it's valid to extend the concept of infinity to the physical universe. Many ancient and modern mathematicians, physicists, and philosophers didn't believe in the logical possibility of an actual physical infinity. Among them are Aristotle, Gauss, and Wittgenstein. For example, in his 2008 article, Universe or Multiverse, co-authored with Bernard Carr, George Ellis expressed this point in the following manner. What has been forgotten here is that infinity is an unattainable state rather than a large number. Its character is totally different from any finite number and is a mathematical rather than a physical entity. According to David Dilbert, the infinite is nowhere to be found in reality, no matter what experiences, observations, and knowledge are appealed to.
While others, like MIT physicist Max Tegmark, argue that a physical infinity is possible, it's no small claim that the multiverse contains an infinite number of actual physical universes. This position involves taking one side in the unresolved philosophical question about the reality of an actual physical infinity. If someone, based on philosophical considerations alone, doesn't believe in an actual physical infinity, they'll have problems with the multiverse right from the start. And even if someone accepts the philosophical possibility of an actual physical infinity, the actual reality of a physical infinity is a significant claim that demands real evidence.
While we thought this point is worth mentioning, we're going to grant multiverse scientists the philosophical possibility of a physical infinity. As you'll see in later episodes, the idea of an infinite number of universes will create serious scientific problems for multiverse theory. All that is coming later. In this episode, we'll focus on evaluating multiverse scientists' evidence that an infinite number of universes actually exist.
Before we do that, someone might suggest that a multiverse theorist can definitely avoid the whole problem of an actual physical infinity by merely positing a functional infinity. That is, an extremely large but finite number of universes. In the above referenced article, Bernard Carr responds to George Ellis as follows. I agree with George's argument against physical infinities. However, we do not need an infinity to validate the anthropic principle, just a large number.
Carr means that as long as the number of universes is at least as big as the odds of attaining all the constants by chance alone, multiverse theory is capable of explaining fine-tuning even though the number of universes is not actually infinite. Keep in mind that the number would have to be gargantuan, more than a trillion, a lot.
While Carr is right that on a theoretical level, a huge finite number of universes can explain the constants by chance alone, on a practical level, all versions of the multiverse that attempt to explain fine-tuning posit an infinite multiverse. This is because it's extremely difficult, if not impossible, to provide genuine scientific support for a large but finite number of unobservable parallel universes.
This is based upon our point last time about the burden of proof. Scientists can't just posit a multiverse containing trillions of unobservable universes without any support. Rather, multiverse scientists attempt to support the existence of these parallel universes by extrapolating from the known laws of physics in our universe to infer the existence of other universes.
This is most often accomplished by extending the theory of inflation, using the model of eternal inflation, to posit a process that continually generates more and more universes with no natural stopping point, and hence yields an infinite number of universes.
Don't worry if you don't know what in the world Aaron is talking about. We'll have much more to say about inflation in the next episode, where we'll discuss eternal inflation in depth, as it's multiverse scientists' primary method of establishing the infinite multiverse premise. Our main point for now is that all of physicists' actual attempts to support the infinite multiverse premise involve an actual infinite number of universes, not merely a very, very large but finite number of universes. A finite but gargantuan number of universes might be philosophically preferable, but it's even less supported by scientific evidence than an infinite multiverse.
And there's another reason why multiverse theories always posit an actually infinite multiverse instead of a functionally infinite multiverse.
That is, while a large finite number of universes can perhaps explain fine-tuning of the constants and the initial conditions by chance alone, it can't explain the design of the qualitative laws of nature, quantum mechanics, and general relativity. This problem has nothing to do with explaining the numbers associated with these laws, but with the special design of the laws themselves.
This is because the only thing that could theoretically constrain the possible number of laws is logic. And as far as anyone can tell, logic doesn't limit the conceivable laws to a finite set of possibilities. Since there are infinitely many possible laws of nature, a finite number of universes wouldn't explain the emergence of our design laws of nature by chance alone. Rather, only an actual infinite multiverse is theoretically capable of explaining the design of the qualitative laws without an intelligent designer.
If you didn't follow that final point, don't worry about it. It's an advanced point. The bottom line is that on a practical level, multiverse scientists always posit an infinite number of universes.
Now that we've introduced infinities, let's consider 3 lines of evidence that multiverse supporters bring to justify the infinite multiverse premise.
The first is from inductive reasoning, the second is based upon empirical evidence, and the third is from the many worlds interpretation of quantum mechanics. We'll leave their strongest support for this premise, eternal inflation, for the next episode.
Besides presenting and explaining these attempted supports, we'll point out two types of problems with each of them. First, we'll explain how these three supports are only supports. None of them convincingly demonstrate the existence of an infinite number of universes. More importantly, we'll show that even though they support an infinite number of universes, they do not address, or sometimes even undermine, the varied multiverse premise, the claim that the constants vary between universes.
This is a critical point. Recall that evidence for infinitely many universes that are all fine-tuned doesn't explain fine-tuning without the need for an intelligent cause. This is analogous to buying trillions of lottery tickets. If you choose the same exact numbers for all of them and they all end up winning, that's difficult to ascribe to chance. But if you choose different numbers for each ticket, then having one winning ticket out of the trillions is easily ascribable to chance.
In the same way, unless you can show that there are infinitely many universes that each have different laws and constants, it doesn't address the problem of fine-tuning.
That being said, let's see the first attempted support. This approach uses inductive reasoning to infer the existence of an infinite number of universes. While scientists don't typically take this route, it often appears in popular discussions about the multiverse.
The basic form of the argument goes as follows. People once thought that the universe was small. Then we observed it to be bigger, causing us to update our understanding of the size of the universe. Then we observed it to be even bigger. Over and over again, every time we think we know how big the universe is, it always ends up being bigger. By inductive reasoning, we can infer that the universe is always going to be bigger than we ever observe it to be, making it enormously large, perhaps even infinite.
For the moment, let's assume that inductive reasoning leads to an infinitely big universe. Still, you may ask, what does this have to do with the multiverse? A theory about infinitely many distinct universes, not merely one big universe.
Brian Greene in The Hidden Reality explains how an infinitely big universe results in what he calls the quilted multiverse. He notes that if the universe were infinitely big, we could effectively treat its separate patches that never interact with each other as separate universes. This essentially becomes one infinitely big multiverse with infinitely many sub-universes.
I hear that, but let's analyze this argument one step at a time. Here's the first problem. It isn't valid to infer from repeated observations of a finite universe that the universe is infinitely big. This is because there's a qualitative difference between a finite and an infinite universe, and no amount of observation of a finite universe can offer any implications about it being infinite. The observation of a finite universe, no matter how big that universe is, has nothing to do with the completely separate issue of whether the physical universe is infinite.
You can't even use induction to argue for a functionally infinite universe by saying that since the universe has always been bigger than we thought, it will always be bigger than we think it is, and it's therefore functionally infinite. This commits the fallacy of induction.
To see this point more clearly, consider an analogy of a huge jar of marbles that you can't see. Let's say you were asked to guess how many marbles were in the jar, and the past 10 times you've guessed, you've been told that there were even more marbles than you guessed. Would that justify your inference that there will always be more marbles than you guessed?
Of course not. While it might take many guesses, eventually you'll guess a number that's bigger than the number of marbles. To posit otherwise is the fallacy of induction.
So you may ask, what is reasonable to infer about the size of our universe, given the fact that the universe keeps being bigger than our observations?
Well, it's reasonable to posit that the universe is bigger than the current observable universe. The argument for this is as follows. It's obvious that the universe isn't smaller than the current size we observe it to be. That's clearly ridiculous. That leaves two possibilities. It's either larger than we currently observe, or it's exactly the size we currently observe. If it were exactly the size of the observable universe and no bigger, that would amount to an amazing coincidence. This is because there's no intrinsic connection between the size of the universe and what humans happen to be able to observe right now. Because positing such a coincidence is unreasonable, we can say that it's highly likely that the universe is bigger than what we currently observe.
So how much bigger is the universe? We simply don't know. And therein lies the issue. It could be a little bigger, or double the size, or much bigger. There's no evidence supporting just how much bigger it is. At this point, proper methodology should lead us to say we don't have enough information to posit any concrete amount. This certainly falls far short of meeting the burden of proof of showing that it's infinite.
The bottom line is that beyond what the evidence indicates, we simply can't intuit how much bigger our universe really is. While we can start speculating on its size, such speculations are beyond the province of science. All other times that science has expanded on our knowledge about the size of the known universe, it has always been based on observations. It has never been extended purely based upon the speculation that it is probably bigger, and certainly not based upon the speculation that it might be infinitely large.
That is, even if you were to accept inductive reasoning to support the infinite multiverse premise, this very line of reasoning undermines the varied multiverse premise concerning the laws and constants. Since the whole line of thinking is predicated upon a quantitative extension of our universe that is always observed to have fixed laws and constants, the only valid inference would be that any new universe would have the same laws and constants as ours. It's illogical to use inductive reasoning to posit a multiverse with different laws and constants, which is a necessary premise for the multiverse theory to explain fine-tuning and design.
That being said, we'd like to concede one point. While an infinite quilted multiverse cannot explain our universe's fine-tuned constants or design laws, it could help explain our universe's highly ordered initial conditions. This is because there's no reason to suppose that all universes start with the same initial arrangement. While scientists have observed the laws and constants of nature to be universal and fixed, we know that the entropy of the universe changes from moment to moment. Therefore, we have no reason to believe that all universes in a quilted multiverse should begin with the same exact initial conditions.
That point is a bit advanced, Aaron. Let me summarize the main point. Even if it were legitimate to infer an infinite universe by induction, this whole approach can't help explain the design and fine-tuning of our universe, because we have every reason to believe that no matter how big it is, our laws and constants are fixed throughout the universe. However, it can potentially explain our highly ordered initial conditions, because it stands to reason that the initial arrangement of distinct patches of our universe would be different from one another.
Let's move on to another potential support for the first premise of multiverse, that there exists an infinite number of parallel universes.
Sounds good, Aaron. Given that the strongest support for any scientific theory is direct empirical evidence, one may wonder if it's possible to find this type of evidence for a multiverse.
The answer to that question depends on what we mean by a multiverse. If we mean a set of parallel universes that can never interact with one another, what we would call causally separate, then by definition we cannot observe these other universes or provide direct empirical support for such a multiverse. However, if a hypothesized multiverse consists of different universes that can interact with one another in the past, present, or future, that is, they're causally related, then observations of these interactions could potentially provide empirical support for this multiverse.
There have been claims in the past, and we're sure that there will continue to be more in the future, that observations have demonstrated the existence of a multiverse. For this reason, we want to clearly explain why empirical evidence of other universes doesn't suffice to explain fine-tuning.
Let's see this point through a concrete example. Over the past decade or so, cosmologists Hiranya Piris and Matt Johnson, among others, have written a series of papers about their search for some indication of the causal influence of one universe on ours. They look for this influence by analyzing irregularities found in the cosmic microwave background radiation, which is light left over from an early stage of the universe's development, leading them to suggest that there could be hard evidence for what they call the bubble collision hypothesis.
While the alleged evidence for an actual collision between our universe and another universe is far from conclusive, we acknowledge that it's theoretically possible for irregularities in the background radiation to indicate the existence of large aggregates of matter that at one point interacted with our observable universe. If so, this would provide empirical evidence that our universe is larger than previously known, or at best, evidence for a few interacting universes. Nevertheless, this is a far cry from supporting the first premise of multiverse theory that demands an infinite number of universes. No observation or set of observations could support that.
Well, not so fast, Ellie. There is a way that scientists try to use empirical evidence of a collision with one other universe to support the existence of infinitely many universes. This is based on a theory called eternal inflation, something we'll discuss in the next episode. Without getting into the details just yet, let's assume that prior to the discovery of a collision with another universe, somehow scientists could show that there are only two possibilities. The first possibility being that there is only our one universe, or the second possibility, that there are an infinite number of bubble universes. If this were the case, then the observation of even one other universe would show that we are not in the only universe. This would then provide evidence for an infinite number of other universes. Of course, this is contingent on the strength of evidence that there are only two possible options, one universe or infinitely many universes.
Good point, Aaron. But even if this were supported, and scientists were to observe a collision with another universe, this observation wouldn't support the varied multiverse premise, the claim that the laws and constants of nature vary from universe to universe. Any universe colliding with our own would presumably have the same laws of physics, insofar as they're interacting within a common physical framework.
While it's not logically impossible, it's hard to understand what would happen if a universe with different laws of physics interacted with our own. Which laws would win out? Would they make some sort of compromise? And if a meta law determined how the different sets of laws interact, that would just beg the question of what designed the universal meta law that governs the interaction between different universes.
The bottom line is that other universes with different laws interacting with our own is highly speculative. The simplest assumption is that even if scientists would one day find evidence of a collision with another universe, that universe would have the same laws and constants as ours. To suggest otherwise would require evidence. Aaron, let's move on to scientists' next support for the infinite multiverse premise.
Okay, Ellie. One of the most often mentioned supports for the multiverse is the many worlds interpretation of quantum mechanics. The many worlds interpretation, first proposed by Hugh Everett in 1957, provides one possible interpretation of quantum mechanics, thereby helping to resolve some of the philosophical problems with quantum mechanics, though it introduces its own set of issues.
Aaron, I know that you're excited to talk about something as complicated as quantum mechanics. Don't worry, everyone. I'll do my best to keep him grounded and focus the discussion on what's relevant to supporting the multiverse.
Enough with the assurances, Ellie. People will love quantum mechanics once they get to know it.
Aaron, let's just keep in mind that our primary objective in this episode is not to explain quantum mechanics.
One of the main problems in quantum mechanics is the famous Schrodinger's cat paradox, devised by Erwin Schrödinger in 1935. This paradox is based upon the strange fact that according to the mathematical formalism of quantum mechanics, a particle can be in two mutually exclusive states at the same time.
Oh boy, Aaron. Try not to make this complicated and confusing.
Okay, I'll give an example. Consider a radioactive atom that has a 50% chance of emitting a particle every hour. According to quantum mechanics, after 1 hour, the state of the atom is a combination of an atom that has emitted a particle, state A, and an atom that has not emitted a particle, state B. If we make many measurements on such individual atoms to determine which state they're in, we'll find that 50% of the time they're entirely in state A, and 50% of the time they're entirely in state B. Nevertheless, until we make the measurements, quantum mechanics says that they're in a combination of both state A and B.
If you think this seems absurd, you're in good company.
Schrödinger thought so too, so he devised the following thought experiment to underscore the problem. Suppose a cat is trapped in a box with a radioactive atom. The setup is such that if the atom emits a particle, it will trigger a device that will release a poisonous gas into the box and kill the cat. After waiting 1 hour, but before making a measurement, the formalism of quantum mechanics claims that the atom is in a combination of state A and state B.
So the atom is in some crazy combined state of emitting a particle and not emitting the particle. What about the cat?
Well, if we take this combined state of the atom seriously, then the poisonous gas is also in a combined state. If the atom emitted a particle, state A, then the gas has been released. If the atom has not emitted a particle, state B, then the gas has not been released. Taking this one step further, if the particle has been emitted and the poisonous gas has been released, then the cat is dead. If the particle has not been emitted and the poisonous gas has not been released, then the cat is alive.
So what happens if we check and see if the cat is dead or alive? It can't be both.
That's exactly the point. If we open the box for further examination, 50% of the time we'll find that the particle has been emitted, the poisonous gas has been released, and the unfortunate cat is dead. The other 50% of the time, we'll find that the particle has not been emitted, the poisonous gas has not been released, and the lucky cat is alive.
Okay, that's normal. So what's the big deal?
The issue is that according to the strict formalism of quantum mechanics, until we make an observation, the cat is in a combination of state A and state B. To say it in plain English, the cat is simultaneously dead and alive. This is known as the Schrodinger's cat paradox.
Well, that doesn't make any sense. So the problem is that quantum mechanics leads to the absurd conclusion that until we open the box and look, the cat is somehow both dead and alive. And yet, there are very strong proofs that demonstrate that quantum mechanics is true. So we can't just say that it's obviously wrong. It's not.
Exactly. That's the paradox. The many worlds interpretation of quantum mechanics attempts to resolve this paradox by saying that reality is not truly a combination of state A and state B. Rather, any time that a particle in the universe can have two possible states, the universe branches into two alternate realities that have no further interactions with one another. In reality A, the particle is emitted, the poisonous gas is released, and the cat is dead. And the observer witnesses an awful scene of a poisoned cat. In reality B, the particle is not emitted, the poisonous gas is not released, the cat is alive, and the observer witnesses a happy purring cat. According to the many worlds interpretation, as time progresses, more and more particles have alternate states, yielding the constant generation of more and more branch universes.
Now I see how this is relevant, Aaron. A cursory glance at the many worlds interpretation implies the existence of many, many different branch universes, a multiverse. Let's evaluate if and to what extent the many worlds multiverse helps explain fine-tuning without an intelligent cause.
The first thing to note is that the many worlds interpretation of quantum mechanics is just that, an interpretation. But there are many other interpretations of quantum mechanics as well. Depending on how you count, there are between 5 and 15 different interpretations. The more conventional interpretation being the Copenhagen interpretation, which says that the act of measuring causes the combined state of the atom to collapse into one particular state in our one universe with no multiverse at all.
The main idea is that since each interpretation of quantum mechanics has its pros and cons, there is no consensus on which, if any, is correct. In his book, The Cosmic Landscape, Leonard Susskind wrote as follows: "The many worlds interpretation cannot be experimentally distinguished from the more conventional Copenhagen interpretation. Everyone agrees that in practice, the Copenhagen rule correctly gives the probabilities of experimental outcomes. But the two theories profoundly disagree about the philosophical meaning of these probabilities."
The point is that all empirical tests supporting quantum mechanics, as well as the mathematical equations of quantum mechanics, equally apply to all the different interpretations.
It should be no surprise that the suggestion that there exist infinitely many alternate universes that don't interact with ours is very hard, if not impossible, to test for.
The inability to experimentally test these various interpretations is why the many-world interpretation, along with the other interpretations of quantum mechanics, are generally considered philosophical, not scientific interpretations.
That being said, let's grant multiverse scientists the many worlds interpretation, putting aside the fact that it is but one philosophical interpretation among many others. Even so, the many worlds interpretation can only support the infinite multiverse premise. But there's nothing in the many worlds interpretation, as it's generally understood, that supports the varied multiverse premise, which is also necessary to explain fine-tuning without an intelligent cause.
The reason for this is that according to the many worlds interpretation, in both reality A and reality B, the laws and constants of nature, as well as the overall order of the universe, remain unchanged. The difference between the two realities is entirely based on whether a specific particle has been emitted or not, and consequently whether the cat is dead or alive. So rather than having an infinite number of universes that each have different constants and laws, the many worlds interpretation gives an infinite number of universes, each of which is essentially identical to the universe from which it was formed, except for that one particle.
Despite this type of particular difference, all the worlds of the many worlds interpretation are equally fine-tuned. There is nothing in quantum mechanics itself that would suggest otherwise. As such, while the standard understanding of the many worlds interpretation may support the existence of many fine-tuned worlds, it doesn't support a varied multiverse that can explain fine-tuning.
In his 2003 Scientific American article, Parallel Universes, physicist Max Tegmark expresses this point about the many worlds multiverse, what he calls a level 3 multiverse, as follows. In short, the level 3 multiverse, if it exists, adds nothing new. Just more indistinguishable copies of the same universes, the same old storylines playing out again and again in other quantum branches.
So if you hear people say that quantum mechanics supports the multiverse, they mean that the philosophical many worlds interpretation of quantum mechanics supports the notion of an infinite number of fine-tuned universes. This can be confusing because most people don't distinguish between this idea and an infinite varied multiverse that could actually help explain fine-tuning.
Despite this limitation, it may be possible to extend the many worlds interpretation to explain the ordered initial conditions of our universe. The reason for this is that while the overall order of our universe remains unchanged by each branching in our universe, it is conceivable to develop a theory of quantum gravity that applies the many worlds interpretation to the Big Bang itself. This theory would then posit that every possible initial state is realized in a separate universe. If one were to accept this extension, then our highly ordered initial conditions would most likely emerge in at least one universe.
However, even if this path were successful, this extension alone cannot explain the problem of fine-tuning of the constants or the design of the laws.
To establish the varied multiverse premise and thereby address fine-tuning, some physicists, following the lead of Brandon Carter in 1974, suggest going one step further. They attempt to modify the many worlds interpretation by extending it to the laws of physics themselves. These physicists speculate that just like quantum mechanics says that a particle can exist in different states in parallel universes, perhaps the laws of nature and their constants could also exist in different states in parallel universes. Leonard Susskind explains as follows. Carter's early pioneering idea for synthesizing the anthropic principle with the many worlds interpretation was this. Suppose the wave function includes branches, not only for some ordinary things, as location of an electron, the decay or non-decay of the neutron, or the life and death of a cat, but also for different laws of physics. If one assumes all the branches are equally real, then there are worlds with many alternative environments. Somewhere in the wave function, the constant equals this number. Somewhere else, it is that number. We live in one tiny branch where the value of the constant is consistent with our kind of life.
That was a tough quote, Aaron. Let me try to simplify it. Essentially, Carter's imaginative idea was to extend the craziness of quantum mechanics from merely applying it to physical matter to applying it to the laws and constants of nature as well. This is obviously a major conceptual leap. But if these speculations were true, then the modified many worlds interpretation would not only support the infinite multiverse premise, but also the varied multiverse premise.
While this might sound like a good idea, there's nothing about quantum mechanics that in any way suggests this extension. Whether or not you like the standard many worlds interpretation, it's at least an attempt to make sense of the difficulties posed by the scientific observations of quantum phenomena. At least it offers solutions to the problems and paradoxes that plague the more conventional interpretations of quantum mechanics. On the other hand, there is no justification for modifying and extending the many worlds interpretation to the laws and constants of physics themselves. It's not suggested by any evidence, it doesn't explain any observed phenomena, and it doesn't resolve any problems or paradoxes inherent in quantum mechanics.
Simply modifying the many worlds interpretation to apply to the constants and laws of nature without any evidence or justification is no better than the mere speculation that perhaps the constants change at the far reaches of our universe. Adding the language of quantum mechanics would only make this speculation more justified if something about quantum mechanics actually implied that the laws and constants were different in the different universes. Without such evidence, invoking the many worlds interpretation is merely a sophisticated way of suggesting that maybe the varied multiverse premise is correct. However, maybe doesn't satisfy the burden of proof needed to support a multiverse explanation of fine-tuning.
Hey, you know what, Ellie? That wasn't too bad. I think we got the main points across pretty clearly.
We certainly tried, Aaron. Let me see if I can put it all together. Using the many worlds interpretation to support multiverse theory has three problems. First, the many worlds interpretation is only one of several possible philosophical interpretations of quantum mechanics. Second, the standard many worlds interpretation only applies to events within our fine-tuned universe. To extend it to the Big Bang itself, and thereby explain our highly ordered initial conditions, is a speculative theory that has yet to be worked out. And finally, the many worlds interpretation is an interpretation of the laws that govern our design and fine-tuned universe. To suggest that something similar applies to the laws and constants themselves is mere speculation that can't provide evidence for the varied multiverse premise. Without justifying this claim, the many worlds interpretation is at best a support for the infinite multiverse premise, but not for a varied multiverse that can explain fine-tuning.
Not bad, Ellie, but the summary is kind of repetitive and just makes the whole episode longer.
Aaron, people like summaries. It helps them process what they've just heard and lets them know what to walk away with. In fact, now that I've summarized the problems with using the many worlds interpretation to support multiverse, I'm going to sum up the entire episode.
Another summary? There's got to be a rule against that. You can't do 2 summaries in a row.
Aaron, even if there were such a rule, your comments have certainly created a healthy interruption between them.
You're a funny guy, Ellie. Summarize away.
Thanks, Aaron. In this episode, we discuss 3 main lines of evidence that multiverse scientists bring to support the infinite multiverse premise. While each one offered some support for this premise, none of them were conclusive. First, while inductive reasoning allows us to posit that the universe is most likely bigger than we observe, in no way does it justify positing that it's infinite. Second, while it's theoretically possible that scientists will one day observe a collision with another bubble universe, that wouldn't support the existence of an infinite number of universes. And finally, while the many worlds interpretation of quantum mechanics posits an infinite number of universes, it's only one of many possible philosophical interpretations of quantum mechanics.
Most importantly, none of these 3 lines of evidence justify the idea that the laws and constants are different in other universes. Insofar as they're all based on extensions of our known universe and its fixed laws and constants, all 3 would seem to imply that even if there really are other universes out there, they would still have the same design laws and fine-tuned constants as our own. Meaning, at best they show that there are trillions of lottery tickets, all having the same lucky numbers. While this may be interesting in its own right, it doesn't shed any light on fine-tuning and design.
Aaron, it's nice to hear you joining in on the summary, and even using my lottery analogy. Welcome aboard! In the next episode, we'll discuss multiverse scientists' strongest line of evidence for the infinite multiverse premise, eternal inflation. So stay tuned.